Hey guys, so today I'm just going to try to make a quick little video explaining the relationship between Coulomb's law and electronegativity. If you don't know what this is from any of your other classes, that's fine. I'm going to try to explain it. I'm talking fast because I really want this to be short. First of all, I do not think that this is necessary for the curriculum. It's not going to be on any tests. But the thing is, this is a fundamental property, characteristic, whatever, of the universe, okay? You zoom in deeper, you look really closely, it doesn't get any closer than that, as far as I know. And so, that is just total bedrock in terms of understanding, okay? If you can connect this to this here, you are, like, solid. It doesn't get any, well, why does this happen? Well, just because this is the way it is. And I think that's cool because even though with chemistry, it's, pretty small, you can just you can just kind of memorize that, oh, this is the way things are, and it's pretty close to bedrock, I think. This really is as deep as it gets. So I think, on top of being a little interesting, maybe I think this is might actually be important. Okay, so now let me explain this equation. You got KQQ over R squared. This is the electromagnetic force, EMF. Okay, electromagnetic force. So you got K, QQ over R squared. Q is the charge of one thing. For this intents purposes of this thing, we're going to say that that's an electron, charge negative, -1, whatever. Because that's what electronegativity is. Okay, Q2, that would be the charge of this nucleus. Okay, over R squared, the distance in between the two things that are attracting each other, the distance between the nucleus and this electron. And K. K is just something that we use to convert whatever number this gives us into a unit that we like. We like force in units of newtons. Okay, so now let me move on to this. Okay, helium, charge of 1 plus. You could just got your 1s orbital. Okay, beryllium, that's charge 4 plus in the nucleus. And you got your 1s orbital, your 2s orbital. They're pretty far away. Okay, oxygen, 8 plus. You got your 1s orbital, your 2s orbital, and your 2p orbital just a little bit further away. And neon, same deal as this, except when this guy gains an electron, he goes way out here, okay? So, now I'm going to explain. As you go from here to here, you notice there's really only two variables that change, okay? You got the charge of the nucleus, this guy right here, Q. This guy's going up one by one, and you got the distance between, where the valence layer is and the nucleus. Okay, that guy's also going up. And so you're like, well, yeah, that fits what this guy's trying to tell us. Let me also say, this force, the force the nucleus has on the electrons, that is electronegativity. The bigger the force, the bigger the electronegativity. So we're saying, how does this grow and shrink as we go down and to the left on the periodic table? Because I think we know electronegativity is higher up and to the right, goes down and to the left. So let's see here. So hydrogen has electronegativity of 2.1. Helium, why is helium like 0? Why is helium totally 0? He's got one more proton. This guy goes up by 1. So why doesn't it go up? Well, the reason why is because for helium to gain an electron, he has to go to that 2s orbital all the way out here, okay? So let's just say, for all intents and purposes, that this distance doubles, okay? So you got this guy goes up by 1. This guy, goes up by 2. What's 2 squared? 2 squared is 4, okay? So the top might be 1 bigger. The bottom, might be twice as big. Next time when he has 2 and he goes up to 3, it'll be just one proton bigger. This guy is a square, and then you get this thing going where you got a graph. Okay, you want to see a graph? This is what a linear graph looks like. Electrons are going up one by one. Okay, distance goes like this. Yeah, so that's that exponential function versus linear function. I'm sorry, I'm trying to go fast. I don't know if this is totally good. So let's talk about so beryllium, right? Beryllium for this guy to, so lithium, he gains with beryllium, okay? And you might think that's weird because beryllium, he's got to jump this gap, right? He's only got one extra proton, he's got to jump this gap. Well, the thing is, because it's just a p suborbital, it's close. You know, this is the s orbital, this is the p orbital. It's close. It's not that big an energy, it's not that big an R gain. As it turns out, the gain in R is actually less than the gain in Q, okay? The thing is, so now I'm just going to try to wrap this up. As you move along here, from here to here, you're getting a linear increase. You're getting a 1 by 1, boop, 1, 2, 3, 4, 5, 6, 7, increase in your protons in the nucleus. And we know that each jump from here to here, each new shell, I don't know by how much it gets bigger, but the idea is it gets bigger by, it jumps a lot. And you've got this R squared here saying, okay, you want to double this guy? You want to double the Q? Let's also double the R. Well, now you got, you know, you're literally plotting this linear guy over a square. And for those of you guys, you know, who ever played with squares, 2 times 2 is 4, times 4 is 8, times 2 is 16, times 2 is 32, and it just times 64, 128, 256. It goes up real fast. I'm sorry, that last part was kind of rambly. I don't know if I got my point across. I'm gonna be honest, you guys. What is there for me to be honest about? I'm just gonna cut this last part out. Thank you guys for. I hope anyone found this interesting. You know, please leave a comment. Oh, one more thing. Neon, right? Why is neon 0? I already explained this with helium, but it's like it's going up and up and up and up. Geez, fluorine is the highest one. Well, the reason why is because neon's only got one more proton, and then he's got this big jump to the next shell. That's just a kind of example of something I've said lots of times. Sorry, this video is 7.5 minutes. Hope you guys, whatever. I hope you guys might have found it helpful or enjoyed it or whatever. Have a good day.